Welcome everyone. To this short session. I was busy the hour before, so that's why I could not teach both hours. So welcome from your Easter holidays. I hope you had some time to rest, or if not, to catch up with all the things that you have to do. One thing before we continue, I think I'm going to go a bit refresh what we were doing because it has been a long time, so I hope you still remember a bit what this course is about. Before that, the next exercise, there is one set of exercise missing, okay? And we are going to I'm going to publish that probably on Wednesday or Thursday next week, okay? And then you will have 2.5 weeks to do it. So if we look at the calendar, I will publish it probably on the 14th, and then you will have the end of the semester, the end of all the lecturing is on the 26th, okay? So probably you will have until Sunday to deliver the exercise, okay? That's the plan. And it's going to be about, we're going to do next week on Wednesday, we're going to do an example of the snow white field. We're going to do compression analysis to calculate how the field operates with a compressor. So you will have to repeat the same for one of the cases that you have already analyzed. Gulfax, I think, was the exercise set 3. I think you had to analyze Gulfax. So you have to apply to, and then there is going to be one task about optimization or maybe pumping. I haven't decided yet, but let's see. But that's the plan. So publishing next week, and then the delivery will be by the 1st of May. Okay, not April. Okay, so let's see. So before that, anyone had any question about the homework or something that was burning inside of you during the holidays that you wanted to ask, and you could not use the email? You had your hands tied, or okay. Yeah. So let's see what we were doing. I think that if we look at the last class, that could give us a hint. So we were talking about measures to ways to prolong the plateau, or we were saying in a more general way, production enhancement techniques. Okay. So we talked what could we do from the reservoir side. We could provide a better pressure support. Okay. Injection of water, injection of gas. We could also improve the deliverability of the formation, okay? And we talked about some methods. There might be some other, okay? We see basically increasing the constant in the IPR. Then we talked about the tubing, okay, and the flow lines. We want to maybe increase the size, okay, so to reduce the losses there. But there was something very important, that if we have the particular case of gas with some liquid, okay, if we make it too big, remember that the velocity of the gas goes down, and then the gas cannot take out this liquid from the well, okay, or from the flow line, whatever it is. So we have to be very careful with this special case. Then we say, okay, we can install all kind of things in the well. Okay, we can put ESP, gas lift, rod pump, jet pump, progressive cavity pump. Okay, we can inject diluent. Okay, we can put gas lift, plunger lift, okay, but all the time taking into account the economy. Remember, what makes different subsea from any other case is the cost. If we want to do any change in an onshore field, probably we can just go and say go ahead and do the change. We have to do an intervention. It won't be so expensive like in the subsea case. Subsea or offshore, you have to mobilize a lot of equipment, a lot of people to do the work. So that's actually, the cost is very high. And one thing that I forgot to include, we went down to these two options, okay, subsea processing and subsea boosting. And we had also one more, that was to reduce separator pressure. Okay, we are all the time, I'm not sure if I mentioned that last class, but maybe not. All the time are producing against the pressure, and that's the first stage. That will be the first stage high pressure separator. Okay, so in consequence, if we lower that pressure, well, we will be able to produce more. But I have told you before in the past that, you know, this option, we don't like it too much, because usually this pressure, there are many other processes downstream that we are cutting. Okay, we are kind of not looking at all the things that happen downstream the separator, but there are a lot of processes that happen there, and they are going to be impact if we change this pressure. Okay, but for some cases you are able to lower it. For example, Snow White, they are going to lower the separator pressure, I think from 2020. Okay, they are going to snow it. They are going to lower the separator pressure, okay, just as a measure to obtain more from the reservoir, to obtain more production. But that's not something that is typically done unless you have a lot of, unless you don't have many downstream processes that depend on that, or you are planning to compensate somehow, let's say putting some boosting equipment downstream to increase pressure. Okay, but that's not something that is typically done. Yeah. Okay, subsea processing, I'm not going to talk too much about it. It's a new trend. Statoil has this subsea factory. You can go and read a lot of presentations, PowerPoints, and see nice videos, animation. Basically, to perform separation, perform primary separation, processing, okay? And that could mean separation of oil, gas, and water. Okay, that could mean also after you have this oil, gas, and water, so this is subsea. Let's make some more space. Okay, that could mean also that you that you do some water processing, processing and disposing. Disposal. Okay. That you do re-injection gas treatment. Okay, that basically is got drying and then re-injection of the gas in the formation. Anything else that I'm forgetting? Well, there might be many things, okay? We're not going to cover all of them. And as I told you, if you are interested, probably you saw something in those of you taking subsea production systems. Probably you get more information about it. So there are more here, okay? But basically, the main idea is to kind of take part of the things that should happen in the platform or should happen in the surface of the sea, to take and put some of the things back in the at the sea bottom. Okay, and then you reduce. Remember, the platform, the vessels, they're usually a very packed environment. Everything is there and everything fits perfectly. And if you want to put something else, it costs. Okay, or it's a big modification to the structure. So really, it saves a lot of space, a lot of cost. Okay, to put everything down, and then you can also address some advantages. For example, okay, are that if you have problems with slugging, okay, you have these transients and they're causing a lot of problems, back pressure on your wells, you can eliminate some flow assurance issues. If you have, for example, water separation, remember that water is what causes hydrates, okay, and if we take it out of the equation, then we don't have any problem. So it helps to eliminate, or at least to mitigate, flow assurance. Okay, if in the case of the water, is very important for fields, for example, that are producing 80%, 90% water, you have to take all of that water to the surface. That's like maybe 300 meters in the Norwegian continental shelf, okay? And these 300 meters, they account for how much? How many bars? 30 bar, okay? 30 bar extra pressure drop that you have on the wells. If you can dispose of that just at the sea, at the bottom of the sea, then you you will be able to produce much more, or to produce in plateau mode for a longer period. Okay, so it's reduce, unnecessary, reduce or eliminate. Okay, of fluids, for example, water, but it could also be gas. In the case if we want to inject gas back into the formation, most of the times we have to take the gas up, then we have to process it, compress it, and take it back down for injection. If that's the case, if you manage to separate at the sea bottom, then you don't have to do that. Then one of the most important things that it helps is allows to do single phase pumping or boosting. Okay, allows to implement either liquid or gas. So this one reduces back pressure. Okay. But if we separate before, remember we began to see last time that we have multi-phase boosters, okay, that they are dealing with the mixture of gas and liquid. But if we manage to separate, then we can use just regular boosters, either a single phase pump or a compressor. Okay, we don't have to be going to this fancy equipment that can deal with both phases. And yeah, there are a lot of things, but just so you will have a kind of a general view of the panorama. And usually remember that we have to be able to control every process. Okay, remember that now we don't have access if we are separating. Let's say if it's a gravity separator, it's a vessel. Okay, we have to be able to do all the functionality that we were able to do on the platform. We have to be able almost to do it subsea. If a problem happens, we have to do troubleshooting, we have to retrieve certain equipment, we have to be able to do almost everything that we had with the equipment here, with the equipment at the sea bottom. So that's also a challenge. And then we go to the part that the lecture of today is a bit devoted. It's subsea boosting. And let's first talk about what are the advantages of subsea boosting. Okay. But first, I just want to make a comment just before that. That remember why the goal or the main goal of all of these measures are. Okay. If we are working in production mode, do you remember already this production mode A and B, or you already forgot? Yeah, you remember? Okay, B was initially, let's say this is the queue of the field with time. Initially, I began production. Okay, I began to put wells in the stream. I began to start up wells, and then I get to a maximum production and begins to decline. Okay, so that's typically for a field producing in mode B. Okay, actually in the class we were plotting only from here. Okay, from in previous lectures, but we have when we are drilling and putting wells into the system. So that's actually we have a kind of a ramp up period. Okay, and the inclusion of these subsea boosters in such a system, they might be able to accelerate production. Okay, that we are able to produce more. That's without any booster. And when we have the boosters, we are able to produce more early. Okay, and we are able also to recover. Let's say that we already produce earlier. Okay, we produce fluids earlier. I think I have a nice figure someplace. Yeah, we'll copy it later. And then the other option, if I'm operating in production mode A, okay, that was a plateau production. This is boosting. Okay, so this is no boosting. This is just to confuse you. I changed the color so to see if you are paying attention. Okay, the main goal in this case is just to prolong the plateau. Okay, prolong plateau. And that's the example that we are going to do next Monday or Wednesday. Next Monday. We're going to talk about, in the case of Snow White, how to use compression, subsea compression, to prolong the plateau. And if you see, really, these two, they have what is fundamentally different in the way I design my boosting strategy in the two cases. Okay, one of them, the boosting has to be in place from the beginning, okay, or very close to the beginning. So I have in the design phase, I have to already say I already have to contact the company to say I want this kind of booster with this capacity, how much it's going to cost me. I have to include already that in the budget, okay? So here I have to include booster in the field design phase or development. It already has to be there included from the beginning. I already have to accommodate all the facilities for that. But while in this case, let's say the plateau, the natural plateau is 15 years, okay, or 10 years, then I can delay all the activities related with acquiring the booster, with installing the booster. They can be delayed. I have to accommodate or think that my system has to take this new equipment, okay? But all the decisions and all the technicalities, all the design, all the engineering can be delayed in time, okay? So booster engineering and logistics. In this case, I have to include them from the beginning. Okay, yeah, let's better go to the next page. Okay, so we're going to talk about the advantages, or this is very general, the advantages, some of the advantages of having subsea boosting. And some of them are to reduce cost. Well, the first advantage is to actually to increase production, okay? Okay. Then also we want to increase tieback distances. Okay. Let's say we have an existing asset, an all mature asset that is here, let's say, and now there is a new discovery or there is a new reservoir unit located someplace, okay? The distance feasible to tie back is it has been expanded due to subsea boosting, okay? Initially, if I depend only on natural flow, maybe the distance can be only 20 to 40 kilometers, okay? But if now I put here a booster to help the stream to go all the way to this old facility, then I can expand and I can increase the tieback distance. Okay. Then also one thing is I don't need any pre-separation of fluids. Well, in the case of multi-phase boosting. Okay, I will still be able to increase the energy of that stream with a multi-phase booster. Here increase production, or also you can maintain. And also that there is one really big advantage of subsea compared to platform or compared to a vessel. That is that the real estate is much cheaper. Okay, you really don't have any limitation. You can buy or put anything that you want on the seabed. Nobody's going to give you hell. Okay, but if you want to put it topside, the same equipment topside, then there will be a lot of conflicts. So real estate is cheap. Okay, subsea, then topside. And one other thing is that the cost, low cost, compare with other production enhancement alternatives. Okay, for example, we talked about that a bit last class, with to put equipment on the well, ESPs, to put gas lift. That implies that we have to go and do an intervention on the well, we have to remove the tubing, and we have to change the completion. Okay, if we have 20 wells or 30 wells in a typical field, that's going to be very, very expensive. Maybe sometimes it's a less expensive alternative, and it's going to be have the same, more or less the same effectiveness, to install a subsea booster. Okay. Yeah, and then some, of course, not, we have also some disadvantages. Okay, and mainly is the cost of the unit. Okay, cost of the unit, and also the cost of deployment, and also the cost of modification of my existing facilities. Or existing production system. Okay, and as you will see very soon, it's not only the equipment that you say, okay, I just install the pump and that's all. There are a lot of other things around it. Okay, remember that the pump has to be controlled, so you need a control module. There has to be also some safety barriers. Okay, also that needs power, electrical power. Okay, you need also to measure, so it needs instrumentation. So if you can only think that it's just a simple pump and that's all. It has a lot of things around it, and even sometimes the space or the requirements of all the other things around, they are more costly than the equipment itself. Okay. Then we come to another problem, that is the maintenance. Okay, this unit, of course, is, remember, everything that moves, okay, or that there is a movement inside, probably is going to fail. Okay, in the future. So maintenance is an issue that we have to take into account, and maintenance is really related to accessibility, and it's a cost, okay, and reliability. For example, it's not the same to install a subsea booster here in the North Sea, where we don't have very high water depth. But if we go to the Gulf of Mexico, that we have to go 2.5 kilometers down to reach the pump, that might be a big issue. So reliability is very important. And then another issue is that if we are talking especially about multi-phase, there is a big uncertainty on the performance. Why? Just because it's complex. Okay, the manufacturer can go and measure the performance of this equipment in the lab. Okay, but then when they put it with real fluids, with the real field, under real conditions, it might give something else. It said, okay, this should give you, I don't know, an increase of 120 bar or an increase of 60 bar, and then you take it and actually gives you 50. Okay, so that's one of the things, the uncertainty in the performance. And as we try to improve our measurements, improve our models, we are trying to get closer and closer, or to have a better prediction of what will be the actual performance. Okay, yeah, so roughly those are the advantages, and they are really, or should I put it, okay, so in general, in boosting, in general, there are two boosting principles, okay? Two principles to increase the energy of a stream, okay? And one of them is, how do they call it? Positive displacement. And the other one is the rotor dynamic. Okay. So there are very clearly split two families of pumps, two families of boosters that have two completely different ways of operating. And I guess this sounds similar. This sounds familiar to you, I guess, from all previous courses, I guess. Okay. Positive displacement is based on the formation of cavities. So formation of cavities. That carry the fluid from inlet to outlet. Okay. Like that's a very typical case is just a piston pump that I have done, I think, the drawing some time ago here in class. Okay, when the piston goes up, okay, this is the piston, and this is a cavity, and here you have two valves that they can open on this direction or on the other direction. Okay, when this one goes to the left, it's going to be closed, and when this one goes to the left, it's also going to be closed. Okay, when I move the piston up, then it creates some kind of a vacuum in the cavity. Okay, and then this valve is going to close, but this one is going to open due to this vacuum that I form in the cavity. Then the fluid goes inside of this cavity, and then when the piston goes down again, then this valve is closed and this valve is open.
Excuse me.
Yep.
I guess you have to change the sign. Both valves have similar positions.
This one goes up.
No, I'm not talking about the piston. The valves, inlet and outlet valves.
But so what are you saying that?
Like if a piston moves up, then there was a vacuum in the chamber.
Okay. Then this one closes.
Then both. In this case, both will close and both will open at the same time.
When you go up, this one is closing,
And
right?
that one is
This one is opening.
no.
Yeah. If the valve is, if I have here a pressure that is lower, pressure 2 is lower than pressure 1. So this is making some force in this part that is greater than the force on this side. Okay, so it's going to open, right? Or no? Yeah? Or when the pressure, the piston goes up, this pressure becomes P2 becomes less than P1, okay? And then the balance in the valve, this pressure, let's say that the area is fairly equal, okay? So I'm have in one phase acting P1 and in the other phase acting P2, okay? So the resulting force is going to force to open the valve, yeah? Okay. Should have brought some, I forgot to, okay. Okay, so that's the principle. You have a cavity that is formed, and then you allow a fluid to go to this cavity, and then you push this fluid out of the cavity. And a very important element here is these valves, okay? And there are different technologies. I showed you last class, I think, was the positive displacement pump, okay? That has a different principle. There is also the ones that we are going to see here is the twin screw pump. Let's see, I think we can go straight to this video. Okay, so there are two screws that are rotating in opposite direction, and the fluid is going from the sides. The fluid here is represented by these balls in violet. It's going from the sides and commingling to the front and going up. And you see here you have the formation of a cavity that opens. Okay, when the two screws are rotating, there is a moment where a cavity opens, then the fluid goes inside, and then the cavity closes. And then that cavity is moved all the way from the suction to the discharge. Okay? Let's take a picture of that. So one example of that, and the technologies here I'm going to make, there are many pumping technologies, but here we're looking at those that are applicable subsea. Okay, there are many. If you go to topside, there are many other technologies, and especially if you go to other applications like drilling, or there are many more. But for subsea, this is the main one that is used, and it's called twin screw pumping. And it's based on that, on the formation of a cavity, and either the cavity is carried along the unit. And then we have rotor dynamic, also called hydrodynamic pumps. Okay, and here, remember, was the principle that I told you before. There is a sequence, and what is the sequence that we have, for example, in the ESP? If you remember, first was a kinematic change where we accelerate the fluid. Okay, so here we have stage. Okay, something called stage is formed or is constituted by a stage. Okay, and the stage has two main elements. One of them is the impeller, okay, that you recognize, or you know, in a very kind of vague way, that is something that rotates and has all of these vanes. Okay, the impeller, and then also has the diffuser. Okay, so we have a sequence where first we accelerate the fluid, in the impeller. Okay, we increase the velocity of the fluid, so that means that we increase the kinetic energy of the fluid, EK. And then we have another phase that is expansion. Okay, because we don't want to keep all of that energy in kinetic energy. Why? Because then we have erosion, we have many other problems with high speeds. So we want to do is change, increase pressure, that means diffuse, change from kinetic energy to potential energy. Okay, and in this case, this form of potential energy is pressure. Okay, and that's done in a diffuser. Okay, don't have space here, but if you have 0.1 and you have a diffuser 0.2, the pressure in 2 should be greater than pressure in 1, and the velocity in 2 should be less than velocity in 1, just because of the expansion effect. And remember, this expansion, we have to do it as smooth as possible, because if we do it too abrupt, then we have that the fluid is going to detach from the walls and it's going to create turbulence, it's going to create swirls, and that's going to give us a lot of problem. Some characteristics of these two pumps is that this particular pump, the twin screw pump, okay, so we didn't talk about, yeah, let's finish first with the twin screw pump. Usually is for low rates, okay, than hydrodynamic pumps. Okay, the other, but one good thing that it has is that the delta P can be higher, okay, delta P higher than hydrodynamic pumps. Okay, that means also I can pump not affected or is slightly affected by the viscosity. That means especially important now in the future that comes a lot of fields with heavy fluid that have high viscosity. This is not so affected by high viscosities. Okay, and yeah, but usually remember that the load rates are small, and also one thing is that it needs some liquid for cooling. So it might not be exactly suitable when you have pure gas, okay? When you have high amounts of gas, high GBF, not good for high GBFs. Yeah, and other thing is that doesn't tolerate well solids. Okay, remember we have, if you see these screws, they are tied together and they close and open by the interaction between these two. If there is a grain in the in between, okay, and it's big enough, then it can cause, so it will just get stuck, okay, or it will cause erosion. So it is not very doesn't tolerate solids, okay. That means it's not very good with sand. Okay. In the hydrodynamic rotor dynamic or hydrodynamic boosters, not pumps, okay, okay, so we can use this for the whole range, okay. If we say GBF, this is GBF, and we go from 0 all the way to 1, where this is pure liquid and this is pure gas, okay, we can use this pump almost up to here, okay, almost up to 90, I think 0.9, okay, 90%. We can use this pump in this range, this booster in this range. Okay. Then in the rotor dynamic we have really two main differences, again we have two main subdivisions, or I could say three, but we have, depending on the type of the impeller, we have radial impeller, we have mixed flow impeller, or we have axial impeller. Okay, radial impeller, I think you have seen already with the ESPs that the fluid goes in the center and then changes direction abruptly and then goes 90 degrees and goes on the outer side. I think we have a picture someplace. Okay, that's a twin screw pump. Yeah, we can take it from last class maybe. Okay, like this type. Okay, that the fluid goes through the center and then it goes out, And then we have axial impeller that they actually the fluid goes in the same direction. Okay, it's not changing direction. Where is it? Okay, like this type. Okay, that the fluid, if I can make it just bigger so you can see, the fluid goes all the time. When it enters is the same as it leaves. Okay, it goes in the same, following the same axial direction, but it has to follow, of course, certain veins that will allow it to. So here we have yeah, we have impeller, diffuser. We will talk just right now about that pump, that kind of pump. Okay, and then we have mixed flow, that is actually a combination between the two. That I don't think I have a good picture here, but actually the we can take it from last class maybe. Okay, that goes not exactly on 90 degrees, but it goes someplace in between. Okay, this depending on the type of impeller, and remember this also makes a very big change on the type of the pump. Okay, because if we use a radial impeller, we have to put again this collector to take it to the next stage. Okay, we have to do this arrangement. If we use axial, we just put one next to the other. Okay, so it's much simpler. And if we use this, we have to use also something like on the radial impeller, that we have to redirect the fluid back to the next stage. Okay, so it creates, it's very important that this creates a very significant difference in the construction of the machine. And also, in a very similar way, the GBF, if we talk about GBF from 0 to 1, okay, pure liquid to pure gas, usually these kind of impellers that are radial, they are good only for GBF less than 10%. Okay, not more than that. It's like the ESPs, they don't tolerate more than 10%. These kind of impellers that they are GBF less than 30%, and these are usually quite flexible. They can go all the range of GBS from purely liquid to purely gas. Okay, GBF between 0 and 1. So why, if we have something that is very universal, why we want to go to the other two that actually have limitations? Okay, it's because the delta P that I can achieve here is much smaller than the delta P that I can achieve with one of the radial or mixed flow machines. Okay, usually delta P of the axial is much less than what I can achieve with a delta P of a radial or delta P of a mixed. Okay, if I want to achieve the same delta P, I have to put more stages. More stages means putting the machine longer. Longer means more material, more possibilities of failure, more structural problems, more costly the equipment. Okay, but if I use these kind of machines, then they will have a higher delta P, but if I have some gas, it's going to cause troubles. And why is that? Well, basically, I have a figure here that we can use to. Is because in these machines, or at least in the radial machine, it acts almost like a separator. Okay, it tends to separate the gas from the liquid inside the machine. I have that figure here. And you recognize this view, right? It's from the front. Okay, the fluid enters here and then it goes to the side. Okay, it's kind of a front view. If we cut, remove the cover of the impeller, then we will be able to see that. And actually, there is a separation of the gas from the liquid that happens in the action machines or in mixed flow machines, but it's not so pronounced. Okay, it's not such a strong separator. Okay. Okay, so I think that's yeah, we will talk about next class. I'm going to talk about the technologies. Yeah, I can put them very quickly here down. There is one main technology for multi-phase pumping. For multi-phase, there is one clear technology. That is called the helicoaxial helicoaxial pump, okay, sometimes abbreviated HAP, okay, and that one is using not any radial or mixed flow, but it's using just axial, and it's very, you'll see, let me find the picture very quickly. Okay, it's actually this type up here, and that's the preferred, the most common multi-phase pump. Some of them in the world, they are twin screw pumps, but most of them, they are helicoaxial pumps. And if you see here, this is how the impeller looks like, and you see why it's so torched. Okay, the fluid has to come from here, and that's the exit, so it's almost like, you know, changing direction completely. Okay, and that's because it helps, is the best configuration that it prevents the separation of the gas from the liquid. Okay, and then you have a diffuser, and then you put a lot of stages one after the other because it's axial, so we need many of them to provide the delta P that we want. Okay, and this is how it looks like in the arrangement. Okay. Of course, if you want to pump just single phase, okay, you want to pump either liquid, that is not very common. Okay, if you think, what do we have in a production system? We usually have multi-phase, okay, no matter what. Okay, we have either gas with some liquid, or we have liquid with some gas, or we have a mixture in between. So usually that's why this is the most common option, to use helicoaxial pump, because it can tolerate most of the range. But if we have, let's say, gas, okay, we have another concept. If we have mostly gas, okay, or if we have mostly liquid, then we can use just like a radial pump, multi-stage pump. Okay, but we are going to talk more about that next week on Monday. Okay, so before we finish, any questions? No? You want to continue? Okay, this is just to present you the technology, the fundamental way it works. Some of you already have this background, okay, but to put you in the same page. But really the main problem, especially with boosting, is the performance. Okay, when you have one phase, either gas or liquid, you know very well how to predict the performance, how to measure it, and especially to have this map, okay, and see if we can be able to operate inside. When it's multi-phase, it's not clear, okay, because let's say in the case of the pump, the delta P, okay, what is the performance plot of the pump? Delta P versus Q, and how it looks like that, okay. Everything in our course is either like this or like that. No, okay. Not to generalize, but it's roughly the truth. Okay, it's like that. But if we add a little bit of gas, okay, a little bit, the gas is disturbing very much the dynamics of the machine. Remember that we have, for example, we have a space like that, and we have fluid coming with this certain velocity. If we put gas, then the velocity does something else. If we put gas, the gas accumulates here and then restricts the passage of the liquid. Okay, it does a lot of bad things to our impeller, to our diffuser, to the whole system. So then maybe we won't be able to get this curve, but we will be able to get, like with the viscosity, something completely different. Okay, the thing is that with viscosity, if it's a single phase, we're able to predict exactly how it will look like. When we have multi-phase flow, no question. Okay, could it be like that? Could it be like this? Could it be like that? Nobody knows for sure. The only way is to measure it, to actually put that GBF, those properties, that viscosity, that density, and measure what it's going to do with the machine. Okay, and our main problem, like petroleum engineers, is that you know, we have a lot of change in the life of the field. Okay, our rate is going to go down. Okay, our GOR is going to go up. Our water cut is also maybe going to go up. There are many changes. So maybe our machine, we know how it operates here at this time one, but then at another time, we don't know. Okay, it has different viscosity, different density, different GBF. So that's where the problem comes from. So what I'm going to teach you now, in next week, is kind of a way to take into account these uncertainties and still plan what your boosting will do to your system. Okay, we won't go in because there is not enough time to the details of multi-phase boosting, but just that you understand how you can plan it, okay, and what constraints you can take into account. But for the final design, you have to go to the manufacturer, that he will measure the machine and tell you if that machine can give you that delta P under that rate or not. Okay. But for a rough approximation, that's what I'm trying to convey, and we will do that next week. Okay. Any question? No. Participation, comment, song, cultural data from... No? Okay. See you next week.